Hi, this is Dane Quinn from the University of Akron, and today I'd like to discuss how to solve multi-degree of freedom systems. And this is for fundamentals of mechanical vibrations. So we'll start off just with a little background. What we're considering is a general unforced conservative system. So this is a system without damping, and it can be written in the following form. We have M, which is a mass matrix, times x double dot. Here x is not a single coordinate but a coordinate vector, so it represents over here, for example, in this example, the x and y together as a vector, x being the displacement of the first mass and y being the displacement of the second mass, plus k, which is the stiffness matrix, times x equals 0. Again, there's no forcing and no damping matrix here. Finally, we also have initial conditions for this problem in the form of an initial displacement and an initial velocity. So let me just remind you what we saw previously. For a single degree of freedom system, we had mx double dot plus kx equals 0, and these are now all scalar quantities. Again, initial conditions. And we were able to find the solution using the method of undetermined coefficients. And it ended up as x naught times cosine omega n t plus the initial velocity, or the initial speed, x naught dot, divided by omega n times sine omega n t. And here omega n is the natural frequency, and it's the square root of k over m. And so again, this was known as the natural frequency. So this is the general solution for a single degree of freedom system. So what we would like is to find a solution, just like we did for single degree of freedom systems, find a solution that satisfies the general equation of motion. So again, it satisfies mx double dot plus kx equals 0 up here in vector form. Okay, so equations of motion. And in addition, it also satisfies the initial conditions. So that's the goal, right? We want to find the function x that works in the equations. Right, so again, satisfies this and meets the initial conditions. And if we can find a function that satisfies those two things, then we say we have a solution. So how do we do that? Well, essentially, we assume a solution. Or at least we assume a form that the solution takes. In particular here, we'll say that, let's assume that x is equal to some vector, and at this point this vector is unknown, e to the I omega t. So here u is a vector and omega is essentially a frequency, but these quantities are unknown. Effectively, they're arbitrary, which means that we can choose them however we want to. So what we'd like to do is see if we can choose u and omega so that this functional form satisfies this equation of motion. So we'll essentially take this and substitute it in. So we need the we need the velocity, and in particular we will need the acceleration x double dot. So here the velocity, I'll just take the derivative of this with respect to time. U is constant, so we end up with I omega e to the I omega t, and then the acceleration x double dot is minus omega squared times the vector u e I omega t. So we'll take this and substitute it in, and it gives us the following: m times x double dot. Well, x double dot was minus omega squared u I omega t plus k times x. Well, x was u e to the I omega t. And we can simplify this. So here we'll essentially factor out an e to the I omega t from both of these terms. And this leads to minus omega squared times the mass matrix times u plus k times u times e to the I omega t. Again, we factored this time function out. And then this equals 0, right? Because the equations of motion equals 0. So really, what this amounts to is making sure that this quantity here in brackets vanishes, right? So really, our quest for a solution amounts to the following. If omega and u, right, these were these unknown quantities that we could choose, or we are able to choose, can be found so that this equation, minus omega squared times m times u plus k times u equals 0, or let's bring this to the other side, ku equals omega squared m times u, then x of t equals u e to the I omega t. So this assumed form is a solution to my original equation of motion, which is mx double dot plus kx equals 0. So really the critical thing that we have to deal with is this. Ku equals omega squared m times u. So if we can solve for u and omega, or if we can choose values of u and omega so that this is satisfied, then we have a solution. So then the next question, of course, is, well, how do we do that? Well, here it is again, right? This is the equation that we need to deal with. And we, right off the bat, notice that one solution is obvious, right? And that's referred to as the trivial solution. So if u is equal to 0, this satisfies this equation, right? Because then the left-hand side becomes 0, and the right-hand side becomes 0, right? So 0 equals 0, that works out. However, there's a problem. And it deals, well, it lies in the initial conditions. Because u equals 0 cannot satisfy general initial conditions. It's known as the trivial solution for obvious reasons, because u equals 0 is trivial. And again, it's important to note that this is a solution, right? But it's not the solution that we're looking for, right? Instead, we want to look for a non-trivial solution. And if you look at this closely, this is exactly a generalized eigenvalue problem. So we've seen eigenvalue problems before. Maybe in a Calc 3 class, possibly differential equations, right? But you should have been exposed to eigenvalue problems previously, but maybe not quite in this form. So how do we go and obtain the standard eigenvalue form? Well, let's take this equation and multiply it by m inverse, right? So we're going to take m inverse and multiply it through. this whole equation. Right? So when I do that, the left-hand side becomes m inverse times k times u equals omega squared times u. And now this is looking closer to a standard eigenvalue problem, right, which is often written as a u equals lambda u. And here, lambda is an eigenvalue, and u is an eigenvector. Together, I'll refer to these as eigenpairs. So, comparing this standard form that we have possibly seen before with what we have here, we essentially see that A, our matrix that we're looking for the eigenpairs of, is simply m inverse times k, and lambda, the eigenvalue, is omega squared. So now, if I can solve this eigenvalue problem and find eigenvectors and eigenvalues, then I can find omega, and as part of that I get u. So let's go back a slide. Remember, if we can solve that eigenvalue problem, then we can find omega and u. As a result, we have a solution, right, of the form x is equal to u e to the I omega t. So let's do that officially, right? So for an eigenvalue lambda that we assume that we can solve for, then the frequency omega is plus or minus the square root of lambda, right? Because remember, lambda was omega squared, so when we take the square root, we get a plus branch and we get a negative branch. So actually we have two solutions here, right? So we have one solution that looks like x of t is u e to the plus I omega t, right? And actually I'll write that as e to the square root of lambda times t. And we have a second solution that looks like x of t is equal to u e minus I square root of lambda t. Right? And here, going forward, I will always assume that omega is plus square root of lambda, and then I'll just add in explicitly the positive or negative value here. So now, with these two solutions, it's a linear problem. So that means that I can use superposition, and I can combine these two things, right? So in particular, I can say that x of t is u times, and then again I can also multiply by an arbitrary constant, right? So superposition says that I can add these two solutions together and multiply them by constant values, right? So we'll assume that one of the constants is c1, right? So and then e to the I omega t, and c2 would be the second arbitrary constant, minus I omega t. And again, this is superposition. But we don't really like exponentials with complex or even imaginary exponents. We'd much rather use Euler's identity and write this in terms of sines and cosines, right? So we can show that this reduces to a sine omega t plus b cosine omega t. And here, this is Euler's identity, or making use of Euler's identity, which was e to the ix, is cosine x plus I sine x. Essentially, these two constants have to be complex conjugates of one another. So if that's the case, then we recover a real valued solution here. So to summarize, if lambda and u, that is an eigenpair, and that's kind of what I call the two of them together, of the matrix A, which is M inverse times K, then we can identify a frequency omega as the square root of lambda, and we have a solution of the form x is equal to the eigenvector times A sine omega t plus B cosine omega t. So this is a solution to our multi-degree of freedom problem, which was mx double dot kx equals 0. Right, so this kind of summarizes how we go about solving multi-degree of freedom systems. We essentially identify this characteristic matrix, M inverse K, or in fact we'll work with this eigenvalue problem, this generalized eigenvalue problem directly. But finding that eigenpair, then we can form the general solution. Alright, so now let's look at how to actually solve eigenvalue problems. So the general solution is determined by what's known as the characteristic equation. So this eigenvalue problem, which again is Ku equals lambda times mu, has a non-trivial solution if the following holds true. The determinant of k minus lambda m, right, so if we form this matrix, and again lambda here is still unknown, and we set that determinant equal to 0 and solve for lambda, then we have a solution. So this equation is known as the characteristic equation. Again, lambda here is unknown, so that's what we're solving for. Now, a couple of facts for an n degree of freedom system. Right, so n is the degree of freedom. These matrices are n by n matrices. Then we find that the characteristic equation is an nth order polynomial. So a 2-degree of freedom system, which is what we'll primarily focus on, leads to a second order polynomial, or just a quadratic equation, which of course we know how to solve. Higher order problems, right? So a 3, 4, 5 degree of system equation or system would lead to polynomials that were 3rd, 4th, and 5th order, right? So those are at best difficult to solve, and typically we would solve those numerically. Right? The other important fact is there are n solutions. Right? So if we have a second order polynomial, then we have 2 distinct values of lambda. Now I will remind you that when we use lambda, we actually took the square root and we formed 2 additional values of omega. So each value of lambda will give you 2 values of omega, basically plus lambda, or plus square root of lambda and minus square root of lambda. And then we actually have n distinct values of the eigenvalues. we typically order these so that lambda 1 is the lowest eigenvalue, and that's going to be less than or equal to lambda 2, which is less than or equal to all the way up to less than or equal to n, where again n is the degree of freedom of the system. So then, once the eigenvalues are found, the different eigenvectors, and again there are n eigenvalues, and so there will be n distinct eigenvectors. So these are determined directly from the original problem, right, which was k times u, in this case u sub I, is lambda I m ui. So this is how we solve these multi-degree of freedom systems. We form the eigenvalue problem. We determine the characteristic equation, right, from the determinant of this matrix. And then we go and solve. Once we've solved for the lambdas, we go back and solve for the eigenvectors. This all works out if you use any of the different forms of the eigenvalue problem. In particular, we'll typically use this form, but it also works out if we use the more standard form, A, where A is m inverse times k, times u equals lambda u. The only reason I kind of prefer this is that I don't really like taking matrix inverses. And if I use this general form, then I can use m directly. And m would come from the modeling of the system, Lagrange's equations, for example. And I don't have to take m inverse. So I find that is one less step that I have to deal with. So let's look at an example, right? So here it is. So this is the example we saw earlier. We've seen this previously in some of the modeling that we've done. Let's take a two-mass chain, so k and m, and then a second element with m and k attached to that. And x and y measure the different coordinates of the two blocks. The resulting mass matrix is given here, as is the stiffness matrix. Again, one of the previous examples that we did, in particular with momentum balance, I looked at this exact system and derived the equations of motion. Right? So if you need a refresher on that, you can go back to one of the earlier lectures, or maybe just do this with Lagrange's equations. But now let's assume that we have the model, right? So again, m x double dot plus k x equals 0, and let's go and solve. So we need the determinant. We need the characteristic equation, right? So we're looking for the determinant of k minus lambda m equals 0. So again, that's our determinant. And really what it ends up amounting to is the determinant of the following matrix. Well, k minus lambda m, we get 2k minus lambda m in this first element. We have minus k and minus k. And then in the last element, we have just k minus lambda m. And this has to equal 0. So remember how we do determinants. Essentially it's this times this, and then minus that times that. So we multiply the two diagonal components together, and then we subtract off the off-diagonal components. And this is for a 2-degree of freedom system only. For 3, 4 larger degree of freedom systems, the determinant's a little more complicated. But here, essentially, this reduces to 2k minus lambda m, right here, times k minus lambda m, minus these two multiply together, so that's minus k squared equals 0. Or, expanding this out and writing it more as a quadratic equation, we get m squared lambda squared minus 3km times lambda plus k squared equals 0. So here we can solve this, right? Quadratic equation. This has the following solutions. And I've done a little bit of algebra. I factored out a k over m from the resulting solution. But essentially we have 3 plus or minus the square root of 5 divided by 2 times k over m. So these are my two solutions for the eigenvalues. I have the plus branch here, and then I have the minus branch. Okay, so here it is again. Just to kind of summarize the mass and stiffness, characteristic equation. These are my solutions, and then when I evaluate this quantity, I get 0.382 times k over m for one solution, and that would be lambda 1. And then 2.618 times k over m for lambda 2. So now I want to go and calculate the eigenvectors. Well, recall that the eigenvectors u1, u2 are their elements, right? So my characteristic, or well, my eigenvalue problem was k, so 2k minus k, and k, times u, right? So u1, u2 equals lambda times m. So the mass matrix is just diagonal here. And then u1, u2. All right, so again, this is ku equals lambda times m times u. So here, let's just go and sort of expand all this out. So this gives us two equations. 2k times u1, right, so this element times that, minus k times u2 equals lambda m u1. And then the second equation is minus k times u1 plus k times u2 equals lambda m u2. Now it turns out that for these values of lambda, right, these special eigenvalues, then these two equations are not distinct, right? They are in fact linearly dependent, which really means that they are, even though they don't look it, they're the same equation. So effectively I just have one equation here, but two unknowns. So I can't solve uniquely. I have too many unknowns. What I can do is solve for one of the unknowns in terms of the other. Right? So what we'll do here is solve for u2 in terms of u1. Now, in general, with higher degree of freedom systems, we always have one linearly dependent equation in this eigenvalue problem, assuming that we have solved for lambda properly. So if I had a 5 degree of freedom system, I would actually just have 4 equations here. And again, I'd be able to solve for 4 of the unknowns in terms of one other one. So we always have kind of one too many unknowns or one too few equations when I go and look at this eigenvector calculation. So doing that, right, let's just look at the first equation here. I could just as easily choose the second equation and I'd get the same answer. But looking at the first equation, we can solve for u2. Right? So u2 here is equal to 2k minus lambda m divided by k times u1. So when I go through and figure out what these eigenvectors are for the different values of lambda, if we choose lambda 1, so lambda 1 here will be the negative branch or the smaller of these two. we find that u1, 2, right? So the first number here is going to denote which eigenvalue we're dealing with. And we solve this as 1 plus the square root of 5 divided by 2 times u11, which, if you work out and simplify, it's 1.618 times u11. Likewise, do the same for the second eigenvalue. So that's lambda 2. We get u22 is now 1 minus the square root of 5 divided by 2, u21, which in this case becomes minus 0.618 times u21. Notice that I can't completely specify these, right? So because u11 is arbitrary or u12 is arbitrary, right, these eigenvectors are not specified. It's only the direction that is determined. So kind of summarizing, right, we have lambda 1 is k over m, 3 minus the square root of 5 divided by 2, which again was 0.382 times k over m. Lambda 2 here is k over m, 3 plus the square root of 5 over 2, which again is 2.618 times k over m. And here, the first eigenvector is 1, and then 1 plus the square root of 5 over 2 times u11. Right, again, u11 is just u11, u12 is this quantity. And then looking at the second eigenvector, we have 1 and then 1 minus the square root of 5 over 2 times u21. Now, the eigenvectors have arbitrary magnitude. So for now, we'll just set u11 and u21 equal to 1. We could make them anything that we wanted to. And again, for now, that's convenient. So this is equal to 1 and then 1.618. And this one reduces to 1 minus 0.618. So we have solved for the eigenvalues and now the eigenvectors. So let's go back and look at the general solution. Again, here is omega. Omega was the square root of lambda, right? So we basically just take the square root of those eigenvalues. Right? This was lambda 1, this was lambda 2. And so the general solution is a combination of these two solutions that we found. So x of t here, which again was the displacement of the first block, which was x, and the displacement of the second block, which was y. Notice that this is a vector and that's a scalar. It can be written as the sum over all of the individual solutions that we found, right? So lambda 1, u1 gives me a solution. Let's go back another page. Or 2. Right? So given a value of lambda 1 and u1, we have a solution. Well, given a value of lambda 2 and u2, we have another solution. So again, it's a linear problem. So I can use superposition. And I can add all of these things up. So the ith solution sine omega I t plus b, and a and b are arbitrary constants, times u sub I. So this term is essentially represented as x of I, and it's known as the ith mode. Each one of these is a distinct kind of mode of operation or mode of vibration for the system, and we'll see that on the next slide. And we can add together the response of these individual modes. Right? So just kind of spelling this out, we end up with A1 sine omega 1t, B1 cosine omega 1t, times U1. U1 was the first mode. So actually let's go ahead and write that out. So that was 1.618. And then the second mode looks like A2 sine omega 2. So omega 1 and omega 2 are definitely known from the eigenanalysis. U1 and U2 are definitely known from the eigenanalysis. That's 1 minus 0.618. Right? But these other constants, A1, B1, A2, B2, are used to fit initial conditions. That was the other part of the initial problem statement. There was the equation of motion, and there was the initial conditions. So we've been dealing with the general solution, and then at the end we would still need to find A1, B1, A2, B2 to solve for the initial conditions. Right, but the important thing here to remember is the general solution which is this whole thing, is a combination of the individual modes. And each mode will have its own frequency, right? Omega 1, for example, or omega 2, for example, and its own mode shape or eigenvector, right? So these eigenvectors really tell us the relative displacement of the different coordinates. So if you just look at this first mode, for example, we have a time-dependent piece out front that's, sines and cosines, and then the response of x, the first block, has essentially relative amplitude 1 to that function, and the response of y has a relative amplitude of 1.618 compared to that function. So again, these eigenvectors really tell us about how the coordinates move relative to one another. So for example, the second one, right? The first element is 1 and the second element is minus 0.618. So I've tried to kind of represent that graphically here. Right, so if I look at the first mode, it's got a frequency of, again, 0.618 times the square root of k over m, and the following mode shape. So now looking at this, if the amplitude of the first block is 1, then the amplitude of the second block would be 1.618. It's not to say that the amplitude here is 1, because of course we have this time-dependent function, but the ratio of these two things is as shown. Right? The second block, when it's operating in this first mode, moves 1.618 times as much as the first block. Notice, in addition, that they're synchronous. Right? So they have the same frequency. They move in the same direction. Right? And they're sort of lockstep together. compare that with the second mode. Now notice that the second mode has a higher frequency. Instead of 0.618, it's 1.618. So the frequency of the second mode is much higher, right? It oscillates faster. And if I look at the response, if I look at the mode shape, again, if block 1 is moving with amplitude 1, then block 2 is actually moving with amplitude minus 0.618. So not only is it smaller, it's negative, which means that these two blocks are now out of phase. Essentially, they would move in such a way that as the block 1 is moving right, block 2 is moving left, right? So they'd be coming together, and then they would be moving apart, and they would be out of phase relative to the ground. While the first mode is referred to as an in-phase mode. So both of these blocks are moving in the same direction at all times. And again, second mode, they're moving in opposite directions. The general solution is some combination of these two. However, as we'll see in later lectures, in particular when we look at modal analysis, this way of thinking about things in terms of understanding the response of the individual modes is really very powerful. And it forms the basis of how we address and try to solve and understand the behavior of really large degrees of freedom systems, right? So here, we're looking at like 2, we might do 3 degree of freedom systems in this class. But when you get out to more practical examples, you might have tens or hundreds or thousands. You could have millions of degrees of freedom. And the only way to make sense of a 1,000,000 degree of freedom system is to do so in terms of the vibration modes of the system. Right? So again, this idea of system modes and eigenvectors and eigenvalues is really, really very powerful for our analysis of multi-degree of freedom systems. Okay, so that's it. That's how we solve multi-degree of freedom systems. Thank you very much, and I will talk to you again. Take care. Bye.